Hi everybody. In part 2, you're going to see what is simple linear regression. So by the end of this week, you should be able to describe a simple linear regression. You should be able to draw a line of best fit. You should be able to estimate the value of a dependent variable for a given value of independent variable. Okay, so let's start with what is a simple linear regression. Simple words, it is a way to model a relationship between an independent and a dependent variable. In other words, it is a statistical tool that allows us to summarize and study a relationship between independent and a dependent variable. So let's go back to our example from part 1, that is the data, bivariate data, that is between the weight and the cholesterol level. Yeah, let's go back to the same example. Okay, so there, if you want to predict the cholesterol level for a given weight of an adult, you can use simple linear regression to predict that value. So what is the use of simple linear regression? It helps you to make forecast or predictions about the data. Okay, so how to find a simple linear regression equation then? Let's see the same example. If linear correlation exists for a quantitative bivariate data, yeah, that is, if there is a correlation, it could be positive or negative, we could fit a straight line through the data to represent the relationship. So for our example, the weight and the cholesterol level, we know how to use scatter plot, and we know how to calculate the PMCC, that is, calculate the value of the correlation coefficient. Yeah, we have seen that in part 1, and we have seen that for this data, the R value was 0.78, and from the scatter plot and from the correlation coefficient, from both, we have seen that there is a positive correlation. Yeah, and you might draw a straight line through the points somewhere like this, or by just simple judgment, you could draw it this way, or each one of us can draw this line in different ways. So which of this is correct? Drawing a straight line through the data by eye will be different each time it is done. And it will be different if each one of you try to draw this line. So which of these is the line of best fit? Which of these is correct? How do you decide that? So how can you be sure that the line is a line of best fit to the data? How can we get the same line of best fit every time? Or how can we get the same line of best fit when each one of us is drawing that or sketching it? Yeah, how do we do that? To find the line of best fit, we apply a process known as simple linear regression. So let's go back to the same example. The linear relationship of y on x is of the form y is equal to a plus bx. Yeah, so it is similar to the one which you saw in semester 1 in mathematics, where you had mx plus c. Yeah, so I can also write this as a is equal to bx plus y is equal to bx plus a. Remember, the coefficient of x is b here, not a. Okay, so here y is the dependent variable and x is the independent variable. Okay, so now you have to find the value of a and b. So this is a straight line with a gradient b. Yeah, b is the gradient, b is the gradient, and a is the y-intercept. B is the gradient. Okay. So for the linear relationship y is equal to a plus bx for quantitative bivariate data, the values of A and B can be calculated from the data using this formula. So don't worry again, this can be directly calculated using a calculator, but for our module, I would like you to use the formula. And there is a similarity. You can see that this is similar to the value which you have seen in the formula for R PMCC. Yeah. Okay. And so B, the slope, is given by this formula, and A is nothing but y bar minus bx bar. That is y bar. Y bar, remember in week 1, y bar is the mean of the data, y, that is mean of the cholesterol level, for example. So y is equal to A plus b x bar. X bar is the mean of the weight of the adults. Okay, so you know how to calculate. If you know how to calculate A and B, then you get the line of best fit. Yeah. So what is A? A is nothing but, because y bar is the mean, so A is nothing but sum of all the y values divided by the total number of bivariate data minus B times sigma x by, yeah, because x bar is the mean of all the x values. Okay, so let's go back to the example. Yeah, so once you find the A and B value, you can find the line of best fit for the linear relationship. Okay, so let's say I'm going to go, these are the data from the calculated value from the part 1. And so you can substitute in that. Why don't you calculate this using your calculator? Good. So you got something like that and a B value of 0.073. So you get y is equal to, now you have to find the A value because you don't know A plus 0.073 x. So let's find the A value. Let's use the formula. Why don't you try that? Use this formula to find the A value. Good. So you substitute the B value, then you know this sigma x, you know sigma y, and you know what is n. N is 12 because we have 12 data pair, yeah, the bivariate data, yeah. And so you get the line of best fit as y is equal to 0.073, x minus 0.55. So that is your line of best fit. Okay. So another important point is, now consider the mean of the weight of the adults. So taking the same data values, you get 75.5. Look at that. So remember this equation, that is the equation for a line of best fit or the regression line. Yeah. So you get your x bar and you substitute the x bar, the A value, this is your B, and that is your Bx minus A. So you have that. So that's your A, and that is your x bar. And when you substitute these values, you get, what is this? That is nothing but y bar. So 59.5 divided by 12 gives you 4.96. So you can see that y bar is equal to bx bar minus A. This is because A is nothing but y bar minus bx bar. We have seen the formula and now we have seen it is true. Now, this can be rearranged to give y bar is equal to a plus b x bar. So what does it mean? The line of best fit should pass through the mean of the data pair or mean of the bivariate data. So therefore, when we determine the regression line for a set of bivariate data, the line of best fit always passes through the mean of x and y. So x bar comma y bar. Okay, that's an important point which you should know. Yeah. Okay, so we have seen how to describe a simple linear regression. Yeah. Now let's see how to estimate the value of a dependent variable. So the main application of simple linear regression is to estimate the value of a dependent variable from a given, for a given independent variable. Yeah. So let's say that we have our equation for line of best fit or equation for regression line, and we have to estimate the cholesterol level for someone whose weight is 85 kg. Yeah. So 85 kg lies within the collected data. Look at that, 85 kg, the weight 85 kilograms lies within the collected data. So we can use these data to interpret the, or I mean, to estimate the value of cholesterol level. Yeah. So we just substitute 85 for X and then we estimate the value for Y. Okay. So which is 5.7. So either you can interpolate and then find the value, or use this equation for line of best fit, substitute the value and find the, or estimate the value of Y. However, care must be taken when estimating a response for a value of the explanatory variable that is outside this range of values, because we don't know whether the linear model agrees, is it still valid for the data values beyond the collected data values. So for example, if I ask you to estimate the value of the cholesterol level for a weight of 120 kilograms, you cannot be sure whether this model, because this is a model, okay? So we can't be sure whether this model is valid or not. Similarly, if I choose a weight of 40 kg, which is somewhere outside this given range, it is not possible to interpolate or estimate the value of the cholesterol level. But if I ask you, for example, what is the cholesterol level for someone whose weight is 70 kg, yes, you can interpolate. You can interpolate and find the value for the, that is, estimate the value for the cholesterol level. Okay, that's very important. Yeah. Okay, so that's it for in part 2. So see you in part 3.